If you know about solution concentrations with moles per liter, this opens it up to the idea of what's called a titration. And a titration is a cool analytical chemistry technique when you can find quantities of like an unknown compound in a mixture. There's lots of neat things you can do about it. A titration is a really cool technique used often in chemistry. And I'm very proud that at Mount Hood Community College, where our funding is not always the greatest, we can do a titration to just as much accuracy, I would argue, as the people like MIT and Caltech, because it all revolves around a burette, which we have. They have them too and stuff. It's a pretty cool thing. So titrations are kind of neat. Let's look at this reaction right here. And this is an acid-base reaction, which we talked about earlier in this section. The acid is oxalic acid, H2C2O4. It's reacting with the base, sodium hydroxide. Notice that water is created, and you also end up with a salt, and this salt is sodium oxalate. You don't need to know that name, but that's what it is. This is what they call a diprotic acid. It has two acidic H pluses, so that's why you need two sodium hydroxides to balance them out. We end up making two waters, and oxalic acid turns into oxalate. To make that neutral, you add two Na, so it's Na2C2O4. So this is a good example of a titration. If this class that you're in right now is meeting face-to-face, we will probably have a titration lab because it's a really cool technique. If this is a virtual class, then we'll show some examples of what titrations are like because they're kind of cool. This is an example of really how a titration works. And on the left-hand side, you have a ring stand with a burette clamp on it. And on the burette clamp is this long kind of tube, glass tube, and that thing is called a burette. They come in different volumes, but the 50 milliliter burette is very common. And you can see that underneath it here is what they call an Erlenmeyer flask. On the burette, there are really accurate volumes known, and they usually go at the top from 0 down to 50. You can read them usually to 1/100th of a milliliter, so like you could get 50.00 milliliters. They're pretty accurate. Usually what you're analyzing will change colors. So you can see in this example, it arguably starts kind of a blue color on the left, and it gets kind of a purple color. So the purple color in this case would be where you would stop the titration. There has to be some way that a scientist can know when the reaction's done, all right? And this is using what's called an indicator. Indicators are just chemicals that turn color when you get to a certain place. It's a pretty cool process. You can rip through many titrations pretty quickly once you get used to it. Pretty cool stuff. Let's pretend that we're going to do a titration here. And we take 1.065 grams of oxalic acid, which you can measure out on a scale, and you put it in the little Erlenmeyer flask and you titrate it with sodium hydroxide. And our sodium hydroxide needs 35.62 milliliters of sodium hydroxide to get to the equivalence point, which in a good titration means that the moles are equal to each other, and it also usually is where the color change happens. We can use this information to calculate the concentration of the sodium hydroxide, and this is kind of a neat thing. Now, the reaction is down here. Oxalic acid, again, reacts with two sodium hydroxides to make that sodium oxalate and two waters. But the important part will be the 1 oxalic acid to 2 sodium hydroxide ratio. We're going to use that. And again, what we're after here is we're looking for the concentration, the moles per liter of sodium hydroxide. So if we turn the 35.62 milliliters into liters, that's going to be the bottom part, the volume of sodium hydroxide. And we can get the moles of sodium hydroxide by first converting grams of the oxalic acid into moles and then multiplying them by 2. So I'll show you what that means in more detail in the next slide. So first, let's take the 1.065 grams and turn it into moles. So you've got to figure out the molar mass of oxalic acid, add up 2 H's, 2 C's, and 4 O's. That comes out to be 90.04 grams per mole. So 1.065 grams divided by 90.04 grams per mole, 0.01183 moles oxalic acid. Notice we're using 4 sig figs here. So 4 sig figs in, 4 sig figs out, etc., etc. Now, the next step, we're going to turn moles of oxalic acid into moles of sodium hydroxide. And that balanced equation there shows a 2-to-1 ratio. 2 moles of sodium hydroxide for every 1 mole of oxalic acid. And this 0.01183 number is the moles of oxalic acid. So 0.02366 moles of sodium hydroxide are needed to neutralize 1.065 grams of oxalic acid. And that's kind of cool. But the final step is to turn moles of NaOH into molarity or concentration, which is moles per liter. So let's take that 0.02366 moles we just calculated and divide it by the volume of sodium hydroxide in liters. How many milliliters in a liter? If you said 1,000, you're good to go. Well done. All right. We're going to do that a lot, so I'll babble about that once in a while. Yeah, 35.62 divided by 1,000 is 0.03562 liters. So you take the moles of NaOH you calculated, divided it by the volume of sodium hydroxide in liters, 0.6642 moles per liter is the concentration here. And that's really cool. Now, why this is useful to me as a chemist is that in Mount Hood, we're so fortunate to have really cool people in our lab room, and they'll make sodium hydroxide solutions for us, which is cool. So let's say I said, well, make it about 0.6 moles per liter, and I'm sure they would, but how close to 0.6 moles per liter is it? I could then use oxalic acid to get a really high quality many sig fig version to figure out what the concentration was. It's a nice way to kind of really fine tune your things to make sure they're right. Also, if you've had a solution sitting around on the stockroom for a while, it's nice to go through this kind of process just to verify that the concentration is about the same. So you can also use this just to verify what the old solution, like see if it's still the same or has it degraded. Oh, the tricks of chemistry. So let's say we have that standardized sodium hydroxide, and standardized just means that you have confirmed to many sig figs what the concentration is. Let's use that standardized sodium hydroxide from the last problem to determine the amount of acid in an unknown. And heck yeah, let's use the apple, because apples, like a lot of fruits are, and a lot of foods we eat, by the way, are actually a little acidic. Now, apples have malic acid. The formula for malic acid is C4H6O5. Malic acid, like oxalic acid, is diprotic. And what that means, of the 6 hydrogens in the formula, only 2 of them are acidic. And we know that because it takes 2 sodium hydroxides to react with them. So the sodium malate, which is what this crazy thing is, that's left over, you can see has 2 less hydrogens. All right, has only 4 when it had 6 before. The other 2 acidic hydrogens went to make water. Again, this is just the acid-base reaction coming together to make water and a salt. Pretty neat. So we can do this kind of thing, believe it or not, with apples. Let's say we take a 76.80 gram of apple and we mash it all up and we titrate it. And we're going to titrate it with a 0.6642 molar sodium hydroxide we did earlier. And it takes 34.56 milliliters of that solution. We can use that information to find the weight percent of the malic acid. And what that means is how many grams in that 76.80 gram sample, how many grams are acidic, how many of them are malic acid. We can use this information to figure that out. Like before, we're going to do a mole-to-mole conversion. In this case, it's going to be moles of sodium hydroxide turned into moles of malic acid. We don't know how much malic acid is in the apple, but we do know the volume of the sodium hydroxide and the concentration of the sodium hydroxide. So 34.56 milliliters divided by what is going to give us liters? Yes, 1,000. 34.56 divided by 1,000 will give us an answer in liters of sodium hydroxide, and we'll multiply that by 0.6642 moles per liter to get moles. So 34.56 divided by 1,000 is 0.03456. That's the number I used in that calculation. Moles per liter, which is what big M is, times liters is going to give us moles. 0.02295 moles of sodium hydroxide were used in this experiment. The next step is we're going to take the 2 sodium hydroxides per 1 malic acid balanced equation and figure out how many moles of malic acid that represented in the apple. So there's a 2-to-1 ratio. We're starting with moles of sodium hydroxide. So the 2 will go on the bottom, the 1 will go on the top. We're going to multiply that 0.2295 by essentially 1/2, 1 over 2. And we do that because we want the moles of sodium hydroxide out of here. We want the moles of malic acid that's left over. So there's 0.01148 moles of malic acid in the 76.80 grams of apple. So again, it's the same idea from the oxalic acid example earlier, but now we're going the opposite way from the base to the acid. Once we know the moles of the malic acid, 0.01148, we can use that to find the grams or mass of the malic acid in the actual apple. The formula for malic acid is right there. So if you add up 4 carbons, 6 hydrogens, and 5 oxygens, you get 134.1 grams per mole. And that times the mole of malic acid gives you 1.539 grams of pure malic acid. Now notice that the whole apple had a mass of 76.80 grams, and only 1.539 grams of pure malic acid were there. So if you ever have to calculate a percent of something, percent of malic acid in this case, it's grams of the good stuff, grams of malic acid in the top, and in the bottom you put grams of everything times 100%. So to find percent malic acid, 1.539 divided by 76.80 times 100%, 4 sig figs, 2.004%. That's the acid percent, the weight percent, if you will, of malic acid in the apple. So for every 100 grams of apple, 2.004 grams will be malic acid. And that's kind of interesting to know too.